All right, let's get started. So I mentioned this in concrete design. I'm not sure that it totally affected steel, but I want to make sure. So I noticed a typo on my homework 1 solution in concrete, and as a result, some of y'all who are also in concrete design had some deductions that you probably shouldn't have, and so I need some time to sort that out. I said, well, I'm just going to wait and give you that homework back later. And so I'm going to do the same thing with steel. I'm just going to check it over once more, make sure I didn't mess anything up, because I don't want to have you all experience a deduction for a mistake I made. I am human. Now, it doesn't count against the 7 mistakes per semester because I caught it in time. So, just for your, records. You do still have a homework assignment, though, that is due on Friday related to tension members. So you should have more than enough background to do the homework based off of what we've done in here. But I do want to see if anybody has any questions about that homework assignment. Any questions at all about it? Have you started it? I hope. Of course. It's almost done, right?
It is.
So, way this is going to work, just so you're aware, you're going to turn in homework 2, and then I'm going to give you homework 3. Homework 3 is going to be on design of tension members, but it's also going to cover block shear, which we haven't talked about yet, and it's going to cover threaded rods. Once you turn in homework 3, it's time to celebrate. So we have our first exam on homeworks 1, 2, and 3, which is on the stuff at the beginning and on tension members. Okay? So just be aware that that's coming. And so what we cover on homeworks 2 and 3 are going to comprise a big bulk of the exam. So just be cognizant of that. Sound good? Okay. Let's get some background and clarity as to where we've left off and where we're headed. So here's our discussion so far. We have we've been looking at tension members. We have 2 primary limit states so far in strength that we're assessing. That's gross section yielding and net section fracture. Gross section yielding is pretty straightforward. It's just the nominal capacity is Fy times Ag, and our phi value is 0.9. For those of you in concrete design, you saw that phi it's sort of a thing that you have to determine, you have to figure it out. But in steel design, it's much simpler. You just, you'll look it up. Primarily because you're looking at a member of a single material, not 2 materials, and so it's a little simpler from that perspective. So phi is 0.9 for gross section yielding. For net section fracture, phi is 0.75. Because if a member fractures, it's separating, it's a much more drastic failure event than if something just gets a little longer. That's what happens when something yields. It's just experiences permanent deformation, just gets a little bit longer. So we have 0.75 Fu times the net area times U, times our shear lag factor. And we could have stopped there, but really what takes a long time with tension members is you have to understand, well, what the heck is net area and what the heck are shear lag factors. So we spent a good bit of time looking at net area. We developed this fundamental expression that the net area equals the gross area minus whatever bolt holes are along our failure path, so the diameter of the hole times the thickness, plus any necessary stagger factors, S squared T over 4G. And again, remember the code actually just says S squared over 4G, but that's for the length. You still have to multiply by the thickness to get the area. The diameter of a hole, again, is the diameter of the bolt plus 1/8 of an inch. Now for shear lag, we looked that up in table D3.1. Our most common case is case 2, which is 1 minus x bar over L. It's not the only case that we have to apply. I'll go ahead and tell you on your homework assignment, you're going to have to look at other cases, and you're going to have to look at other cases besides case 7, because we did a wide flange in class. You have a channel and an angle on your homework assignment, so there's going to be different cases that apply. And so there's your net section fracture, 0.75 Fu times the net area times U times shear lag factor. And we do have a service limit state, which is the slenderness limit, that L over R has to be less than or equal to 300. And R being your minimum radius of gyration. So that depends on the section that you're looking at. So be cognizant when you're looking up properties on your homework assignment that you're using the right ones. Then we did this example, start to finish. This was a full-blown analysis example. Now, when I say full-blown, we didn't do block shear on this problem. We'll actually come back to this particular example later and look at block shear in example 6. But but for now, we'll just sort of ignore that. And then, this was a good problem. We took a little bit of time on this. So here's our section. We had, so when I say full blown, we had to look up all the properties for the W8 by 24. We had to look up all the properties for steel so we could compute gross section yielding. We had our net area calc. We had the shear lag factors. We recognize there's two cases to consider. So we look at, case 2 and case 7. Case 2, because we have a wide flange with bolts through the flange, we had to look up the eccentricity, which was from an equivalent WT. So it's a W8 by 24, so it's a WT4 by 12. And so here's our shear lag factor. We had K7. We technically didn't need to assess K7 because whichever value it was going to be, we were going to use the higher value anyways. Net section fracture, determined our capacity as the lower of those two. Finally, we did our L/R check and everything was hunky-dory, although we were pushing it. We were right there on the cusp. If that member was any longer, it probably would have failed. Sound good? All right. That's analysis. And to be clear, analysis is an important skill for an engineer to be able to acquire. For instance, in bridge land, many bridge engineers spend their time designing bridges, but they also spend their time rating bridges. Looking at a given bridge and assessing its current condition and basically determining a rating factor. You can think of that as sort of on a scale of 1 to 10. And so rating factors will help owner agencies like a DOH determine, okay, this bridge has a rating factor of 2. It needs to be replaced now. This bridge has a rating factor of 8. It's doing okay. This bridge has a rating factor of 5. We probably need to pay a little bit more attention to that, maybe put some maintenance on it. And so that's when I say rating, it's basically just analysis. You're determining the capacity. So it's an incredibly important skill. But it's also important from an educational perspective because once you understand how to analyze a member, you then know how to design a member. Okay? So in other words, when I say design, I'm talking about selecting the members, selecting the details, so that they're both safe and economical. Now, I want to be clear on a couple things because there's going to be a little bit of a difference between what we do in class and maybe what you would do in real life. Okay? So when we say what we do in class, and I want to make this rule right now, okay? Whenever I say design, what that means is lightest member. Okay? Now, what do I mean by that? Okay? If you had two choices, and those are your two choices, which one would you pick?
45.
The 45, why?
Lighter.
Why is it lighter?
Why is it lighter?
Why the 49? What told you it was the lighter one?
It's 45 pounds per foot.
Exactly, okay? And so the reason why we say lightest member for our purposes in this class is because the lighter member means less steel. And if you're buying steel per pound, a lighter member is less money, okay? So for our purposes in class, we're always going to be designing for the lightest section. Now, I want to introduce a little bit of reality into this so that everybody understands. That may not be necessarily what you do in the real world. Let's take this building. How many beams do you think are in this building? Hundreds, right? Now, what if every single beam was designed uniquely? Every beam had its own shape and own cross-section. Contractor would go to the engineer and say, "Are you crazy? How am I supposed to put this together? You gave me a jigsaw puzzle," right? Instead, what if this building only used like 5 or 6 beams? And maybe there was a couple of them that were different, but by and large, they were all the same. From an engineer's perspective, there are probably beams in that building that are over-designed because some beams are going to be larger than they need to be. But from a real-life perspective, it makes the contractor's job and the steel erection crew's job a whole lot easier dealing with fewer shapes, right? So in reality land, you might design some members with, you might, I guess, a little uneconomically, like with a more oomph capacity than they need to because it would facilitate construction. And then there's all sorts of other issues, like you want to make sure you're picking sections that are available, that meet the current rolling schedule. You know, you don't want to pick a shape and the steel mill's like, "Oh, well, we're not going to have this for 12 weeks, but if you pick that shape, we'll have it in 4 weeks." You know, so it's not as simple as that, but I just want to make sure that everybody's on the same page that from what we're doing, we're going to, we're going to pick the lightest section. Now, I will say steel availability is getting a lot better nowadays. The rolling schedules are a lot easier to access, and it's a lot easier for engineers to figure out what's available and what's not. We might look at that later, but for now, we'll just keep that simple. Sound good? Okay, so for us, lightest section. So we have 3 limit states, and so we have yielding in the gross section, fracture in the net section, and slenderness limits. And so I want to look at how we would design. Okay. Now, design means selecting a member. What do I mean by that? Okay. Let's take a look at yielding in the gross section. Okay. What is our fundamental limit state expression? Okay. Our fundamental limit state expression says our factored resistance must be greater than or equal to our factored loads, right? Okay. In other words, maybe, I didn't put this up here on the slide, but maybe that's an expression for factored loads. And what's our strength? Well, what would our strength be if we were looking at gross section yielding? Well, our gross section yielding would be this, would be Fy times Ag, right? And our phi value is 0.9, okay? So that's our design expression for gross section yielding. Now, if I'm in design mode, if I have a building and I got a brace, okay, I need to design that brace. Okay, I need to design that brace to hold up, 50 kips in dead load, 100 kips in live load, and let's say, that's what I know. Well, I could probably say, well, if it's going to be a wide flange, it's probably going to be A992 steel, or if it's an angle, it's going to be grade 36 or whatnot. So I can probably determine the material properties really easily, just based on the fact if I know I'm going to use a wide flange, or I know I'm going to use a channel, or I know I'm going to use an angle. That's pretty simple. In design mode, what I need to know is this. That's what I need to know, so why don't I just solve? So divide, and I find that AG must be greater than or equal to 1.2 dead plus 1.6 live over 0.9 Fy. Boom. There's design. There's design right there. In other words, I will pick one of these members out of here, one of these, I find one of these members that has a gross area bigger than that, and I know I've met that limit state. Simple, right? That's straightforward. Now, that's our first design expression. Our minimum gross area is the factored load divided by 0.9 Fy. Okay? In other words, when I go and I select a member, I got to select a member that has at least a gross area of Pu over 0.9 Fy. That's one. What about slenderness? All right? L over R has got to be less than or equal to 300. Well, what does that mean for member selection? I probably know how long the member is going to be, because if it's in a building and I'm picking that member, I know how long it is. But if I'm in design mode, I don't have a clue what R is, because I don't know what the member looks like. But that's the point. I'm trying to figure out what member I need to pick. So why don't I pick a member that's radius of gyration is at least L over 300 or bigger? Make sense? So the minimum radius of gyration's got to be L over 300. Simple, right? That's straightforward. Now, what gets funky is this. What about fracture? That one gets tough, because it's not as simple. See, with gross section yielding, I can just solve, and as long as I pick a member that has a gross area greater than or equal to that, I'm good. But with net section fracture, there's a little bit more going on, because what is the net section fracture capacity? Well, it's 0.75 times Fu times the net area times U. And what's the net area? Well, the net area is the gross area minus the area lost due to bolt holes plus the presence of any stagger factors. So it's messy, right? There's no way to really solve for something. But you can ignore the math if you want, and there's no way to really solve for anything that you can look up for a couple reasons. When you open up that manual and look up the properties for a W10 by 45, does it tell you what the net area is? No, it tells you what the gross area is. You then compute the net area based on your connection and based on your parameters and so on and so forth. Okay? Now, if you're in design mode, remember, I have a member here that needs to hold up whatever force. I don't know what the member looks like. because I don't know what the member looks like, you could ignore the math if you want and just look at this. There's really only two parameters that gives us a problem. The first is the thickness. Because if I don't know what the member looks like, I don't know what the bolts are going through. And if I don't know what the bolts are going through, I don't know the thickness to determine the net area. I also don't know the shear lag factor. Remember, the shear lag factor is a function of your connection eccentricity and your whether it's a wide flange or an angle of channel. I have no idea what U is because I don't. How do I figure that out if I don't know what the member looks like? That's tough. Okay? So how do I get around that? Okay? Now, if you recall, we did a little bit of a shortcut. Remember, if you open up the spec says it's 0.75 FU times this effective net area. We never really use that term because all this is just the net area times U. Okay? What I'm going to do is I'm going to make a blanket assumption. Okay? This is complicated and there's no way I can solve for anything, so I'm just going to make a blanket assumption. I'm going to say that the effective net area is 0.75 times the gross area. Or if you want, you can say, okay, our capacity is 0.75 FU, the net area times U. Well, instead of this net area times U, I'm going to say 0.75 FU times 0.75 times the gross area. And so what I'm suggesting is that this 0.75 is a reasonable guess, because remember, what are you doing? You're taking your gross area, you're reducing it to get to your net area, then you're multiplying it by a U value to get an effective net area. Again, I have no idea what the connection looks like. None whatsoever. So I've got to make a guess right now in design mode. So here's the thing. Right now in design mode, we're going to make a guess. We're going to assume that the gross area, or the effective net area, is 75% of the gross area. I'm doing that so I can come up with an equation I can solve for, something simple. Okay? So it's 0.75 squared because there's two 0.75s. One is our phi value and the other is an assumption. Okay? Because I'm making an assumption, I have to go back and check that assumption. I can't just pick a member and say, oh, I'm good. I have to go back and check it. And so the problems are a little belabored. Now, therefore, what we can do is we can select members based off of these two expressions. Our minimum radius of gyration, and then this right here. This is just combining that and that into one single expression. So our minimum gross area and our minimum radius of gyration is is based off of these expressions. So we have some criteria upon which to select a member. Okay? But remember, we're making some guesses. So because we've made assumptions, once we pick a member, we need to go through the exercise of analyzing that member to assess its capacity. Okay? If y'all want to write these down, you can. Do I need to leave this up here for a second? 1 second. That's fine, sir. Sound good? Okay. Now, a couple things that you need to be aware of. First off, how many shapes are in here? A lot. There's oodles of different wide flanges and T's and channels and everything. So in a real life scenario, if I told you, I want you to design me a tension member that can hold up 100 kips in dead load and 300 kips in live. I just said, do that problem. There's 19 people in this class. I could get 19 different answers, and they're all right. I don't want to grade 19 different answers, okay? So what I'm going to do is I'm going to place a little bit of a limit on the problem, okay? For example, in this example we're about to do, I want you to pick a W12. So it's going to be a W12 by something. It might be a W12 by 30 or a W12 by 8 or whatever, okay? So I'm placing this limit on here so that we all arrive at the same answer. In reality, it would be much more open-ended. But one thing I will say about the limits that I place, I try and reflect real life as much as possible. For example, let's say that behind this wall right here, let's say I had a brace in the building behind this wall that went like from down here to over here, okay? Could I feasibly use like a W27 for that? Like, could I put a W27 between here? Remember, what's a W27? How deep is that? 27 inches deep? Can I fit that here? Well, you tell me. I don't think that's 27 inches, do you? So, if we're talking about tension members and we're talking about braces, let's say in buildings, it stands to reason that you would have some sort of depth limitation because you're going to fit that in a wall or in an elevator shaft or somewhere in the building, and it can't be 30 some inches deep or whatnot. So putting a limit like, oh, it's a W12 or oh, it's a W10 is probably a pretty reasonable limit. Also, another thing is if you're connecting that to another member, like you're connecting this tension member to adjacent parts of the building, having those members have similar depths makes the connection very doable. Like, what if I have a W10 section? So let's say that's a W10. So these are the flanges sticking out, and that's the web. And I'm trying to connect that to like a W27. Like, how do I connect those two? That's kind of weird, right? Whereas if I had a W10 connected to another W10, well, I could slap a plate up here, slap a plate down here, and bolt them down. Having the members have similar depths makes the connection make a little more sense. So everybody okay with that? So it's a little bit, I don't want to say outside of reality, but I'm limiting that to where we all get the same answer. Now, we're in design mode. You will never, and I mean never, be able to pick a member that has perfect 100% efficiency. That's not how it works, okay? We're going to do the math, and we're going to say, okay, pick a member that has a gross area of at least 8.5 square inches. And you're going to go to that manual, and you're going to find the closest one. And it might have 8.7 or 9.2, right? So there's going to be some cushion built into that. But how do you know whether or not your design is good, okay? A good way of checking that is to compute its efficiency. And its efficiency is basically the load that's on the beam divided by the resistance, okay? So you can sort of think of this term as kind of like the Price is Right. You want that value to be as close to 1 as possible without going over, okay? If it goes over 1, what that means is that the loads are bigger than the resistance. If the loads are bigger than the resistance, what does that mean?
Fails.
It's going to fail, right? Because it's got more load on it that can hold up. So you want that value to be less than 1, but as close to 1 as possible. A good rule of thumb, and I will adopt this rule in this class, is that if your efficiency is 90% or greater, you don't need to check the next one. You're good, okay? When I say you don't need to check the next one, you'll know what I mean after this example. Does that sound good? So that's going to be our rule in this class. It's also going to be a rule on exams. If you do a problem on the exam and your efficiency is 92%, don't worry about the next one. Okay? Trust me, that'll become clear here in a little bit. Everybody good? All right. Let's get into design. I have a tension member that is 30 foot long in a building. It is being subjected to a dead load of 130 kips and a live load of 110 kips. That live load has already gone through live load reduction, so there's no need to worry about that. And we are going to select a W12 section. When I say select, I mean design. When I mean design, I mean the most economical selection possible. We're going to use A992 steel, which is the most appropriate steel for wide flange sections that you would use anyways. And we're going to use 7/8 inch diameter bolts for this problem. So we're going to mix it up a little bit. No more of that 3/4 inch stuff. walk you through this first part a little bit. We'll start rocking and rolling with this thing. Okay. Now, help me out. We were given a dead load and a live load. What do you think we ought to do with that dead load and live load?
Do 1.2 dead.
Exactly. Because we don't deal, when we're looking at, remember, our design philosophy is LRFD. We don't deal in just dead loads and live loads. We factor them in order to produce a statistically relevant load that accounts for all of our uncertainties. So we call that a factored load. So our dead load is 130 kips, and our live load is 110 kips. So now if you recall, there are two load combos if you've got dead and live that you need to worry about. So one of them is 1.4 times the dead. And the other is 1.2 times the dead plus 1.6 times the live. Now I'll go ahead and tell you the answer to the first one, because that one's simple. That's just 182 kips. What's the second?
$332.
332. So if you're designing, which one would you use? The 332. So our factored load is 332 kips. Now, I want to be clear. That does not mean that the tension member is actually seeing 332 kips. Really what you're saying is it has 130 kips in dead load and 110 kips in live load. So really it's probably experiencing 240 kips. That's not the question. The question is, how certain are you that those numbers are accurate? You can't be 100% certain. And so that's what those dead load and live load factors are doing. The 1.2 and the 1.6 are accounting for uncertainty associated with those events. And you're more uncertain about live load than you are dead load, which is why that factor's higher. Yes, sir.
How do we know dead load if we don't know, like the other dimension of the what W12 is, like the unit weight of it?
Oh, that's a great question. That's a wonderful question. In tension member land, you can pretty much ignore the self weight of the member, because if you look at the self weight of this member, I'm not saying it's not negligible, but the self weight of this member is nothing compared to 130 kips in dead load. It's all about the mechanics. I will go ahead and tell you that for tension members and for members that are loaded axially, you can, at least for the most part, ignore that for the purposes of design. If you have a really, really heavy column, you probably need to consider it. But for design purposes, for tension members and compression members, you can largely ignore it. Beams, however, that's another story. Members being bent, they just tend to be weaker flexurally than they are axially. So as a result, you do kind of need to account for it in self-weight length. And we are actually going to encounter that problem, not just in steel design, but in concrete design. How do you design a beam when you don't know the self-weight of the beam? And so you have to guess. And so you guess a number. And you'll end up coming up with a design. You may have to iterate that design because you guessed that the beam would weigh 50 pounds per foot and it actually weighs 200. So you have to go back and iterate it and check. And so that's just the nature of the beast when it comes to design. But for tension members, we can kind of largely ignore it. That's a great question. Great question. Sound good? Okay. Now, we have A992. We have A992 steel. Okay? So if we have A992 steel, what is Fy? What is Fu? And where do we find those values? We find them in Table 2-4 of our AISC 15th Edition Steel Construction Manual that everybody brought. I actually think everybody did bring it. Nice. That's what I like to see.
Y is 50 KSI and U is 65 KSI.
That's exactly right. And so we'll say Table 2-4. One other thing I'll tell you, you'll get to the point where you kind of start to memorize this stuff because you use it so often. 8992 grade steel is one of the more common steels that we'll use in this class. When we look at columns and beams, we're only going to be looking at wide flanges, and so those will pretty much be constants for the latter half of the semester. So, okay. Now, let's look at our design expressions. Now note, the member is 30 foot long, which is 360 inches long, okay? Don't forget to convert your length into inches, okay? So we have two design expressions. We have an AG minimum, which is, sorry, hold on. So I'm basically pulling these from right here. I wanted to be able to make sure you saw where I was coming up with these. So minimum of 0.9 FY or 0.75 squared FU and PU up top. So maybe on over here to the side, I'll say 0.9 FY. I think I could do that in my head, and that's what, 45 KSI? Is that right? Yeah, 9 times 5. Okay. And then 0.75 squared. Don't forget that that's squared, okay? Because remember, we have one from our fee value and one from our assumption because we don't know what the net area and the shear lag factors look like, so we have to guess something right now. So we'll say this is FU, but again, it's 0.75 squared. So somebody have a value for this? 36.6, you said? Give me one more.
It's 36.56.
36, so say 36.56 KSI. That's good enough. Is everybody okay with that? Do I have a second? Okay. So what we're going to do is we're going to take PU divided by the minimum of those two, so we'll use that one. So, again, why would we use the minimum? Well, I'm trying to solve for the area, how much steel I need, right? So which would result in the worst case scenario? Smaller denominator means higher answer. And so if I'm designing, I want to pick the worst case scenario, the one that's going to result in the higher area. So 332 kips over 36.56 KSI, that equals what?
I
9.08. Do I have a second on that?
Yep.
All right, and that's square inches. Okay. All right. Now let's do the next one. R min is L over 300. So that's 360 over 300. And what is that? Is that 1.2?
Yeah.
1.2 inches. Whoop. Okay. Sound good? So, what this means is this. What were we restricting this problem to? A W12. So therefore, pick a W12 with an AG of at least 9.5 0.08 inches squared. And minimum R value of 1.2 inches. That's what that means. So help me out. Find me a W12 that has these two properties. Now remember, when you're looking at W sections, which R value do you look at? Rx or Ry? I'm not going to help you with that one. You gotta tell me.
I guess it's Y.
Why?
No clue.
Remember, we're looking up R values for slenderness. And the worst case slenderness, the worst case L over R is the one with the smaller r. For W sections, no matter what W section you're looking at, the smaller r is always the one about the y-axis. Okay? So for W sections, you're always going to be looking up Ry here. That may not be the case for angles or for channels or whatever, WTs, but so you need to be cognizant of that. Like WTs, I believe it's RX, or it can change depending upon what the section looks like. Not good?
So it would be a W12 by 35?
I'm asking you.
That's what I said.
That's what he says. What do y'all say?
It's a minimum.
Right? It meets the gross area requirement, and the RY is 1.54. I mean, the RX is fine. So that works, doesn't it? Is that our answer? Are we done?
You need to check the efficiency.
Well, we need to check the efficiency, but there's a couple other things we need to do. We need to verify our assumptions. See, when we did that calc just now, that gross area calc, we didn't look at net area or shear lag factors. We just made a guess. For all we know, this member doesn't work. And the only way to know whether this member works is to just check it start to finish. Okay? So what I'm going to say in the calcs is try a W12 by 35. I don't know whether or not it works, and there is a chance that we do all this math and it doesn't work. Okay? But for now, we'll just go off of that assumption. So you pick that. Why? Because it has a gross area of 10.3 and an RY of what? 1.54?
Yep.
Now, don't change that dial. If we're going to analyze this section, do we need any other properties? Thickness of what?
Flange.
You said flange. Why the flange?
Just put the bolts in.
The bolts are going through the flange. Exactly right. We need the flange thickness. So what is the flange thickness of the W12 by 35?
0.3.
0.3.
0.52.
0.52. Let's say it's easy to look up the one on the wrong column. You looked up the web thickness, didn't you?
Yeah.
Yeah, that's the web thickness. Yeah, that's easy to miss, and that would totally throw your answer. So don't. I mean, I know it seems like not much, but it is. We are also. I'll go ahead and tell you. We are also going to need BF and D. Why are we going to need BF and D? Because of that case 7 in the shear lag table. Okay. So what's B sub F?
6.56.
6.56, and what's D?
12.5.
12.5. So remember, the 35 is how heavy it is, pounds per foot. The W12 is about how deep it is. So it has a nominal depth of 12 inches. Its design depth is 12 and a half. And so if you look at all the W12s, they range a bit, but it's based off of that rolling pattern that it's about 12 and a half. Sound good? Now, we have to analyze this section start to finish. So this is going to be like example 4 all over again. But remember, a lot of calcs that we're doing, we just skipped with that. So we have to verify that. That's why we're doing all of this. So I might go a little fast, but we just did this, so it should be pretty straightforward. Does everybody have everything here? Okay. All right. So first thing we're going to look at is net area. Let me go back and actually copy that image. I want to have that image here, just for reference, so that we're all looking at the same thing. Now, our bolt diameter for this problem was different. It was 7/8, right? So 7/8 of an inch. So what does that mean for the hole diameter?
It's 1 inch.
1 inch, right? So diameter of the whole bolt plus an 8. All right? So somebody tell me what to do for the gross area, or for the net area. I'm asking you. I'm not driving this train anymore, you are. Yes,
Okay, so we're in design mode and everything.
we're in design mode.
How do we tell if we need to add a stagger factor or not?
That's a great question. So first off, let me say a couple things about that. Right now, I told you what the connection looks like. I told you that here's the member. So like if I were to draw this right here in 3 dimensions, in 3 dimensions, I've got 1, 2, 3, 1, 2, 3. Because that's what my connection scenario was. So there's no stagger factor because there isn't any for this problem. That would be my first point. My second point is, right now, for tension members, I'm going to tell you what the connection looks like. You're not going to have to lay out the connection, because after we discuss tension members, we're going to discuss connection design. So for now, I'm going to give you the connection, but later on, we're going to say, okay, how do I actually design the connection? How do I actually arrange that? So for now, just bear with me, and then later on, you'll see how to arrange it. And all of the, the bolt bearing, bolt tear out, bolt, all that stuff, we'll deal with that later. I promise you will have a clear answer to that in a few weeks. It might be a little fuzzy now. For now, I will not make you arrange the bolt pattern. I will tell you what it is. Don't worry. Sound good? That's a good question. It's a really good question. Sound good? We may not finish this example today, but that's fine. We're going to chug along as much as we can. Now, net area. Let's go back to this. So, tell me what to do.
Take the gross area and then you subtract the number of bolt holes times the flange thickness.
Okay, so the number of bolt holes times the flange, so the diameter of the hole times the flange thickness. How many holes am I subtracting? 4. 4, exactly. Samurai sword or lightsaber through the section. 1, 2, 3, 4. Boom. So the gross area minus 4. And so that is 10.3 minus 4 times 1 inch times 0.52. Got an answer for me?
8.22 square inches.
8.22 square inches. Do I have a second on that?
Yes.
Awesome. Okay. Okay. Now this is the same connection scenario as the last example we did. So how many shear lag factors did we need to assess?
Okay.
2. Case 2 and case 7, right? So let's look at that. So shear lag factors. So case 2, we need an X bar and a length. Let's deal with the connection length first. How long is this connection?
8 inches.
8 inches. Now the X bar, what are we going to do? The equivalent WT, but what property from the WT? Remember, connected face to the centroid, and for a WT, that's what? Remember, if you're looking at the W shape, or the WT shapes, we're talking about that property from the top to the centroid. That's what these images here on the top left are for. So if I go from the top to the centroid, what am I looking up? Y bar. Remember, don't look up the Y sub P's. Don't look up that, okay? I will explain what those Y sub P's are by the end of the semester, but for now, just ignore them. So it's the Y bar for an equivalent WT. What is the equivalent WT?
6 by 17 and a half.
6 by 17 and a half. It's a 12 by 35, so half of 12 is 6, half of 35 is 17 and a half. And so what is Y bar for a WT 6 by 17.5?
inches.
1.30 inches. Do I have a second on that? Okay, so that comes from table 1-A. So therefore, U2 is not a band, it's 1 minus X bar over L. It's just not even. Okay, so 1 minus 1.3 over 8.
0.84.
Say it again.
0.84.
0.84. Do I have a second on that?
Yep.
Okay. Now, let's talk about case 7. So you probably want to turn to your shear lag table. Does case 7 apply?
Yes.
Okay, so it's a Y.
3 or more fast.
Three or more facets per line. And how many do we have per line? 3 per line. So we have B sub F. We have D. Okay, so what was B sub F again?
6.56.
And instead of D, sorry, I meant 2/3 of D's. 2/3, and I think that was 12.5. And so, I'm not that good, but probably 8 something. 8.3. 3.3, is that it?
Yes.
Okay. So B sub F and D, that's greater. So U7 is what? 0.85. And which one are we going to use? 0.85. Take the larger of the two. All right. I want to finish this. Well, I tell you what. Let's just power through this real quick. All right. So capacity, because this ain't gonna take long. So we have two capacities. We have gross section yielding. We have net section fraction. Gross section yielding is 0.9 FYAG, 0.75 FUAN times U. So somebody tell me out what's the first one, and we'll do the first one and the second one. So here, I'll fill these values in. All right, so what's the first one?
463.5.
463.5 kips. Have a second on that? And the second one?
340.6 kips.
All right. Which one of these governs? The bottom one. So you're telling me phi PN is 340.6 kips. Now, before we leave, I have two questions. What does that tell you? What do you compare that against?
PN.
Not PN, PU.
Oh, yeah.
And what is PU?
332 kips.
332 kips. What does that mean? I'm asking you, what can you tell me about this selection?
The efficiency?
Well, the efficiency, but I'm thinking basic. That's the strength. And 332 is what we're putting on it. What does that mean?
Beam's good.
Picked the wrong beam, I guess.
The beam's good.
It's good. It's a tension member. I even use beams. It's good. This is how much it can hold up. The 332 is what we're putting on it. This is good. This is a safe design.
97% efficiency.
How much?
97.
97%. What if this was no good? What would you do?
Try the next biggest beam.
Pick the next one. That's what I meant when I said pick the next one, is if this is no good, pick the next one. Okay, so instead of a W12 by 35, you go with a W12 by 40 and do it again. And so design is iterative. Now we have a section that's 97% efficient. What if it was 60% efficient? Go to the next lightest. Remember, we did all this math based off a guess, so you might have to go back and iterate again, or you might have to go and pick the next one. It's very possible, okay? So, but if this problem's 97%, you're good. Don't do any more. Now, there's a couple other things we need to do with this example, but we'll do that on Friday. I've kept you a couple minutes over. I apologize, but that's all I got. I'll see you.